So, welcome back to lectures on engineering mathematics 2, and this is a lecture on Fourier series, and we will evaluate for different functions. So, today we will cover the Fourier series of 2L periodic functions. So, in the previous lecture we have already discussed Fourier series of 2 pi periodic function. So, that is just a generalization of those 2 pi periodic function, and then we will evaluate the Fourier coefficients and respectively the Fourier series for many functions. So, just to recall that Fourier series of a 2 pi periodic function we have discussed in the previous lecture, and suppose this f is a periodic piecewise continuous function on the interval minus pi to pi. So, its Fourier series is given by this trigonometric series a by 2, and then we have the summation over a k cos k x plus b k sin k x, where the coefficients, the so called Fourier coefficients a k, we can compute by this integral from minus pi to pi f x cos k x dx, and similarly the coefficients b k we can compute again with the similar integral having this sign term here sin k x dx, and this k goes from 1, 2, 3 and so on. Here this a k was valid for a 0 as well. So, therefore, this k starts from 0 and then continues to 1 and 2. So, its extension for 2L periodic function will take a similar structure, and we have already discussed the trigonometric system which is 2L periodic in previous lectures. So, here for the 2L periodic function, let us suppose this f x be a piecewise continuous function defined in this interval minus L to L or from 0 to 2L, whatever ways, and it is supposed 2 pi 2L periodic. Then its Fourier series will be given as, so the a naught by 2, a constant term, and then we have this a k, and instead of cos pi x, now we have k pi x over L, and here sin k pi x over L. So, for L is equal to pi, this will reduce exactly to 2 pi periodic function which we have already discussed, and the coefficients are also similar now. So, a k we have here 1 over L instead of 1 over pi. So, 1 over L, and then minus L to L f x, and then here we have the cos term cos pi x over L, and then k goes from 0, 1, 2, 3 etcetera. So, the b k is again 1 over L, and then instead of cos k x we have sin pi k pi x over L, and then k in this case varies from 1 to etcetera. So, this is a more general case now for any 2L periodic function or the function defined in this minus L to L, we can have we can write down the Fourier series. So, now this some examples. The first one, we want to find the Fourier series to represent this function. For instance, the f x is given as minus pi. So, f x is given as minus pi when in the range minus pi to 0. So, this is the function, and then 0 to pi the function is given by x. So, this is pi, this is minus pi. So, that is the given function here from minus pi to 0, it is represented by minus pi, and then the function is given by x in the range 0 to pi. So, we want to, so it is a piecewise continuous function, and we want to write its Fourier series. So, it will be a 2 pi periodic function to whom the Fourier series will converge. So, but just to write the Fourier series we need a function defined in some interval. So, in this case it is given in the interval minus pi to pi, and now we will write the Fourier series, and that Fourier series if it converge, it will converge to this 2 pi periodic function, where in this one period the function will be represented by this given function here. So, the Fourier series of the given function will represent a 2 pi periodic function, and the series is given by this is standard series, because we are talking about 2 pi periodic function. So, in this case we have written this standard series a n cos n x and b n sin n x. So, the a naught we know already, it is a 1 by pi and minus pi to pi f x dx. So, we can compute this integral. So, we have 1 minus pi, and then from minus pi to 0 the function was defined as minus pi. So, we have substituted this, and 0 to pi the function is defined as x. So, if we compute this first integral, for instance, so it is a pi and then we have x. So, 0 minus and then minus x. So, this is minus pi square, and then here pi square by 2 will come from the second one. So, this is the, and then 1 over pi is was also sitting there. So, minus pi square and then plus pi square by 2, and then 1 over pi is there. So, then here we have minus pi square by 2. So, this pi get cancelled, and we will get just pi by 2 with a minus sign, because this was the minus here, minus pi square, and then we had this plus pi square by 2 in the bracket, and the 1 over pi was sitting outside. So, it is a minus pi square by 2 is coming with 1 over pi. So, we are getting this 1 over minus 1 by 2 into pi. So, that is the a naught, and now we will compute a n and b n. So, for a n we have this formula 1 over pi and this f x cos n x. So, again f x is given as minus pi in the range minus pi to pi, and 0 to pi it is given as x. So, we need to compute now these two integrals. So, for the first one we have this pi will get cancelled, and so we have not written here 1 over pi or this pi. So, this pi and this pi gets cancelled for the first one. We have cos n x. So, that will be sin n x over n, and the limits minus pi to 0. For the second one, so we have 1 over this pi outside, and then we have to apply this partial fraction, the partial integration rule. So, here the x is there, and then cos n x will from the cos n x we will get this sin n x by n, and the integral the limits will be 0 to pi, and then minus the differentiation of this x will be 1, and then again we have sin n x over n, and the limits 0 to pi. So, the first one, when we have the upper limit here, sin will become 0, and then for pi also this will become 0. So, the from the first term we are not getting anything, it is a 0. From this second term also, when because of this sign here pi and 0. So, this will again become 0, and the last term will contribute. So, we have 1 over pi, and this sign again will be integrated to get this cos. So, we have the cos n x over n square and 0 to pi, and this minus is adjusted for this integral of the sin n x. So, we have 1 over pi sin cos n x over n square and 0 to pi. So, substituting these limits, we have the cos n pi, which is minus 1 power n, and minus this cos 0, that is 1, and then 1 over n square pi is sitting outside. So, this a n, the coefficient these Fourier coefficients a n are now computed as when n is an even number. So, this will be positive and this is negative. So, this will get cancelled and we will get 0, and when n is odd, so this will be minus and this is minus 1. So, we have minus 2 divided by n square over pi. So, this we have got the Fourier coefficients, the a n, and now similarly we can also compute b n. So, in b n we have here the sine function. So, again, so minus pi to 0 we have pi, the value of the function, and 0 to pi we have the value of the function as x. So, here the first one, this sin pi gets cancelled, sine will be cos n x over n, and this minus will be adjusted for the integration, and then minus pi to 0, and then we have 1 over pi sitting outside, and then again we have integrated this x sin n x. So, x as it is and sin n x became this cos n x with the minus sign, and then minus minus plus again the cos n x over n dx. So, this time this term will not vanish. When the 0 we have this 1 and then minus pi, we will also get cos n pi, which is minus 1 power n, and then in this second case we have 1 over n pi, and here we will get with pi, and then cos n x will give minus 1 power n, and in this case when we integrate this, this will become sin n x and divide by n square. But when we substitute the limits, so the upper limit or the lower limit, because of the sine function, this will become 0. So, that is the contribution of the last integral as 0. And now we can simplify this. So, we are getting 1 over n and 1 minus 2 minus 1 power n, or in this b n for n even, because when n is even, here we will get this minus 2. So, 1 minus 2, the minus 1 over n will come, and when n is odd, so this minus 1 power n will be minus. So, these two will be added, and so we will get this 3 over n. So, that is the coefficient b n we have. Now, coming to the Fourier series. So, we can write down its Fourier series now. So, a by 2 and then these a n cos n x and b n sin n x term, where a 0, a n and b n we have just computed. So, we can substitute these coefficients in the Fourier series, and we can obtain the Fourier series as follows. So, f x we have minus pi by 4. So, a by 2, this will be minus pi by 2, and then we have minus 2 over pi, that is the term will come from when we substitute this a n and b n terms. So, this cos we have just written in this expanded form. So, this is coming because of this 2 over pi was here in the cos. So, 2 over pi is here, and then we will get these cos terms, and then in the sin terms will be coming exactly from the b n. So, in this way we can obtain the Fourier series for a given function. The function was piecewise continuous. The piecewise continuity in the last lecture we have already discussed, that ensures the integrability of the function in this range where we are integrating for the period. So, the a n and b n can definitely be computed if if the given function is piecewise continuous. So, just a remark that it should be noted that the piecewise continuity of a function is sufficient. So, that is sufficient, exactly what I was discussing here, for the existence of the Fourier series. So, for the existence of the Fourier series, what do we need? We need piecewise continuity of the function, because if the function is piecewise continuous, we can get a n and b n, because the function will be integrable. Piecewise continuous functions are integrable in that closed interval. So, that is sufficient for the existence of the Fourier series. So, if a function is piecewise continuous, then this is always possible to calculate Fourier coefficients. That is very clear. Now, the question arises whether the Fourier series of a function converges and represent f or not. That is the question which has to be discussed, and we will discuss in the next lecture. And there we will see that we need some additional conditions on the function, not just the piecewise continuity, but we need some more conditions to ensure that the series converges to the function to the desired values. So, these issues we will take in the next lecture. Now, another remark, let a function be defined in this minus L to L. So, we have a function which is defined in minus L to L, that is all, and periodicity of the function is not required as such to develop the Fourier series, because we need a function defined in minus L to L or minus pi to pi for the special case, and then we can find out a n and b n, and we can write down the corresponding Fourier series. However, if this Fourier series converges, that will converge to a periodic function with the period that 2L. But at the beginning we have a function which is just defined from minus L to L, and if it is not periodic, or we do not have any other information, just the function is defined from this minus L to L or from 0 to 2L, whatever. So, and then we can write down its Fourier series. So, the function is defined, and that is all, we do not have any other information, but we can write down its Fourier series, and then the Fourier series, if it converges, it will converge to a periodic function, and in one period that function will look like exactly this f x, this given function to whom we have written the Fourier series. So, I think that point is clear. However, the Fourier series, if it converges, it will define a 2 pi periodic function on R, and therefore, this is sometimes convenient just to think always that the given function is a 2L periodic function defined on the whole R, but as such it is not required. A function is given in some domain, we can write down its Fourier series, and if this Fourier series converges, it will converge to a periodic function. In one period, the function will be exactly the same which we have used for constructing the Fourier series. Okay, so we have the another example where we will expand this f x is equal to sin x in a Fourier series. So, this sin x function, if we just take a look, it's a modulus sin x. So, it is 0 here, and then at pi it will become again 0, and then since the positive, so it will never go to the negative portion. So, this will be the graph of this function. So, 0 to pi and then 2 pi etcetera, and then we have minus pi, minus 2 pi, and so on. So, here there could be many ways, but we are just considering two cases just to show that the period actually does not matter. For example, here the period of this function is pi. So, if we take period pi, that means the function given in this range here, and write down the Fourier series, or we take a function from this 0 to 2 pi and then write down the Fourier series, both the Fourier series will be same, and that we will demonstrate using this example, for instance. So, this function may be treated as a function of period pi, and we can work in the interval 0 to pi, or we can treat this function as a function of period 2 pi, and we can work in the interval minus pi to pi. So, we will take two cases here. In the first case, we will treat this function as a function of period pi, which is actually the period, the fundamental period of this function. And in the second case, we will multiply by 2 this fundamental period pi. That means, we will take a 2 pi, we will treat this function as 2 pi periodic function, and then construct its Fourier series, and at the end we will realize that it is actually the same, whether we take a period pi or take a period 2 pi or 3 pi etcetera. It does not matter. For the Fourier series, we will have the same Fourier series. So, in the first case, we will treat this function sin x as pi periodic, and then we have, so for pi periodic, that is a general period, it is not a standard minus pi to pi we take, it is a pi periodic. That means, the 2L is pi, and then we have this L as pi by 2. So, a general version of this Fourier series we are going to use now. So, the coefficient A naught, as per the definition, we have this 1 over L. So, 1 over L will become 2 over pi. So, this is 1 over L, outside just 2 over pi, and then we will integrate from 0 to 2L, or from minus L to L. So, in this case we are taking 0 to 2L. So, 2L is pi. So, 0 to pi f x dx, it's 2 over pi. The f x from 0 to pi is just sin x, it is a positive. So, we can remove the mod here, dx, and the sin x will be cos x with minus sin 0 to pi. So, that we will get 4 over pi. So, that is the first coefficient A naught 4 over pi. Now, we will compute A n. So, the formula is given here 1 over L 0 to L f x n cos n pi x L n pi x over L dx. So, here we will take this f x. So, 0 to 2 L, that means 0 to pi, the function is positive in 0 to pi. So, we have a sin x, and then we have cos 2 n x. So, cos 2 n x, how we are getting cos 2 n x? The cos and then n pi x and L is pi by 2. So, this pi gets cancelled and we have 2 n x. So, this is 2 n x, and we can integrate now this. So, 2 times sin A cos B formula we will apply. So, 2 sin this the sum will come 2 n plus 1 x and minus the sign will come with 2 n minus 1 x, and then we can integrate it having this cos at both the places and then limit 0 to pi. Substituting this pi there, we have 2 n plus 1. So, we will get this value 2 there, and here also we have cos then 2 n plus 1 again. So, because we have the 0 also and the pi. So, this is going to be 1, and then again this is going to be when we substitute 0 1. So, we will get this 2 there, and the value after simplification we will get minus 4 over pi 4 n square and minus 1. Well, so what we will get now? So, this is the coefficient for A n, and n is 1 2 3. So, we got the value already. For B n again we have the similar result 1 over n f x, and then we have the sign here for B n. So, we can compute now. So, with the sin 2 n x will come with the sign, and then we again apply to sin A sin B formula, sin 2 n minus 1 cos 2 n plus 1, and then cos will be sin, and again this cos will become sin there. And since the sign is here, whether we put pi or 0 or here also pi or 0, this will be 0. So, at the end we realize that this B n is 0, and this f x we can write down as the A n, which was pi by 2. So, 2 over pi A n by 2, and then we have this cos term only because the B n terms are 0. So, there will be no sin term. With cos 2 n x we have this was the coefficient A n we have just evaluated before. So, we got this Fourier series when we have treated the function as a pi periodic function, or we can just simplify little more. So, here minus this 4 over pi we have taken this outside, and then we got this series here. Well, so now in the second case we will treat this f x as a 2 pi periodic function, because 2 pi is not a fundamental period, but it is also a period of the function. So, we can consider this 2 pi periodic function, and then we have the standard result that A n will be this 1 over pi and then minus pi to pi. So, the result is for A n is 1 over pi, and then we have minus pi to pi, and then this f x, and then we have cos. Okay, it is written here already. So, this minus pi to pi, and when we are talking about f x is a even function, and then cos x is also even function. So, the integrand is even, and then we can write down 2 times, that is 2 times and then 0 to pi, and then we have the function here, but now in 0 to pi the function is positive. So, we have removed the mode, we have sin x, and then we have this cos n x dx. So, now we can apply this formula 2 sin x cos n x. So, sin n plus 1 and sin n minus 1 x, and we can integrate now this sign. So, we will get with minus sign this cosine and this cosine, and again with the same argument. So, we will put first the pi there, sin n plus 1 pi, and then with minus this sin cos 0. So, what we will get, first we have to assume that n is not equal to minus 1, otherwise this will break down. So, we will get this formula minus 1 power n plus 1, and then for 0 we will getting 1 here, and similarly minus 1 power n minus 1, and for 0 we will get 1 there. So, this for n not equal to 1, what we have this formula, which can be further written in a more simplified form. So, when n is odd, this will become 0, and when n is even, this can be simplified to this minus 1 over pi and 4 over n square minus 1. So, a n we need to compute now separately, because this formula, the general one, was not valid for n equal to 1. So, that we can separately do this cos n x cos x and sin x cos x, which is sin 2 x, and then we can integrate this to have this cos, and then we have cos 2 pi and then minus 0, cos 2 pi is 1, and then minus 1 is also 1. So, we will get simply this 0. So, this a 1 is 0, a n we have computed, and for b n, if we write down these Fourier coefficients b n. So, we have this sin x sin n x, and since this is the even one, and then we have odd here. So, minus pi to pi with this odd function as an integrand, this will become 0 straightforward without calculation. So, the b n, these coefficients are 0, and therefore, our f x now after substituting these a n's and b n's can be obtained in this form, which can be again written in a more compact form, having this 4 n square minus 1 and this cos 2 n x term. So, this was exactly the series which we got, assuming it as pi periodic. So, we have considered two cases here. Once we have taken the function as pi periodic, and then we have taken this function as 2 pi periodic, and at the end we have observed that we are getting the same Fourier series, which is very much expected, because the changing this period is not changing the behavior of the function. It is just taking the extra length with having this repeated behavior of the function. So, if we develop the Fourier series of a function considering its period as any integer multiple of its fundamental period, we shall end up with the same Fourier series. That is the conclusion, and we have demonstrated from this example. Also note that in the above example, given function is an even function. So, another observation which we should keep in mind, and later on we will discuss in detail, that this sine function was an even function. So, the sine function here with absolute value, it was an even function. So, around this 0 here, this has the same value as in the negative values there. So, it was an even function, and for the even function, when we are computing the b n, so b n is f x and sine. So, sine is an odd function and f x is an even function. So, then the product is an even function. Sorry, the product is an odd function, because we have the even and odd. So, the product will be odd. So, the b n coefficients, when we computed here this b n coefficient. So, if this f x is even and this is odd, so the product of these two even odd is odd. So, if the integrand is odd and we are integrating from minus pi to pi, then this integral will be 0. So, that is another way of describing this, and not to compute this 0. If this f x is an even function, naturally this b n will disappear, or the vice versa. If we are talking about the odd function, then a n will become 0, and we have to just compute b n. So, if the function is odd or even, we can simplify the calculations, and all either a n will survive or b n will survive. Okay, so, this is the last example we will discuss here. Let f be a periodic function with period 2 pi and defined in this way. So, half in minus pi to 0, and then 1 from 0 to pi. So, its Fourier coefficients, if you compute first a naught from minus pi to 0 and 0 to pi respective values, half and then 1 there, So, we can get this 3 by 2, and then if we compute the a n, again we have to break from minus pi to 0 and 0 to pi, having this cos n x and half and then 1 there. So, again what we will realize that this is 0, and this is interesting because this is not 0 because of this even and odd structure, but this is just appearing, this is just coming to be 0. So, the b n, if we compute, it is coming sign there, and then again we can compute these simple examples, simple integrals, and we will get 1 over 2 n pi 1 minus cos n pi. So, having these Fourier coefficients, the a naught was 3 by 2, a n 0, and then we have the b n, we can write down its Fourier series. So, 3 by 4, this a by 2, and then we have this b n, and then we have sin n x. So, this is the Fourier series of this given function. So, if we just get the idea how this Fourier series look like. So, just recall the function was given here from minus pi to pi as minus half, minus pi to 0 was half, and then the value was 1. So, this was our function. This was our function f x, and then this is the Fourier series we have plotted. Fourier series we have plotted for about 10 terms. So, the terms here we have taken 10. So, this instead of infinity we have taken for instance 10, and we have plotted this graph, and then you can see because we have taken only 10 terms, the approximation is not very good. It is not matching with for example, the given function. It is not converging or seems to converge at this for just for 10 to the given function. But what we do if we take more, terms, for example, if we take 50 terms here, now you can see it is quite close to the function here as well as here, but there is a point here, the discontinuity point, where the function value in this side it was half, and then we have this 1 value. It is a problematic and it is always crossing at this middle value here between this 1 and 1 half, and that exactly we will observe in the next lecture theoretically, that what is the convergence of this series, or in other words, to which function this series converges, because from here as we can see that this is not converging exactly to the given function f x, and mainly on at this point 0 for instance, because if we take more terms from 0 onward it will match, and from less than 0 it will also match to the given function. But what will happen at this 0 point there, which is definitely it is not matching here, it is always crossing this point in the middle. So, that is what we will see in the next lecture, that we will discuss the convergence of the Fourier series, under what condition it will converge, and it will converge to the given function, or it will converge to some other function, and what will be that function. All these discussion will take place in the next lecture. So, here we have the references used for preparing this lecture. And just to conclude, so we have discussed that if f x is piecewise continuous defined on this interval, or it may not be 2L periodic, or it is 2L periodic, does not matter. We can write down the Fourier series, and this Fourier series will converge to a, if it converges to, it will converge to a 2L periodic function. So, this was the more general form of the Fourier series, where these coefficients, the Fourier coefficients, are computed in this way. And we have also seen that if we take its period, any integer multiple of its fundamental period, the Fourier series will remain the same. The Fourier series will not change, and we have also demonstrated with the help of one example. So, that is all for this lecture, and I thank you for your attention.